So let's just jump into. So problem one, block M is supported by pulley system as shown. Other edge of the rope is attached to a square with the following steel plate with side EH fixed to the wall. Alloy bars AC and BCD with thickness of 20 millimeters and depth H are supported by a double hinge pin. So uh, double hinge pin with a bolt diameter DB at A and B respectively. The two bars are also connected by a pin at C. So una, suppose that the side FG of the steel EFQH experiences a uniform uh, horizontal displacement of 50 millimeters to the right due to the weight of the block alone. Lines EG and FH are the diagonals of the square plate and intersect at the center at J, neglecting the change in height of the plate. Determine the shear strain at J between those two lines. So that's the first problem that we have. So, ayan. Um, Essentially, pinapasolve lang dito yung shear strain, and that's given by this equation. Gamma equals pi over 2 minus theta. The idea lang here is that you're trying to get the difference between yung total final like lean ng isang bagay compared to when it was completely upright. Because that's what shear strain measures, angular difference. So, yung pinapa-measure na angle sa atin, sorry, is between FJ and JG. So that's this one. The way we want to simplify this para di na tayo mahirapan masyado is to cut it into a quarter. So magkakaroon ka ng 0.6 dito, which is half of 1.2, and 0.625, which is half of 1.25. This is derived from the fact that 1.2 meters plus 50 mm. Yeah. So then, but since nahati rin yung theta mo, so technically this is theta over 2. So you can solve for theta by essentially getting yung tangent inverse. So this is y, this is x, tangent inverse of that. So syempre may over 2 ka. So you have to first transfer that. And then you will end up with 0.87.662. And then you're not technically done pa after that point. You have to again go back to pi over 2 minus degrees, then degrees. But this has to be in radians. So pi over 2 is the first term, copy lang. This is the term that we found. This is the theta that we found here. And then we convert it to radians using yung conversion factor for degrees to radians, which is pi over 180. Subtracting that, you get gamma equals 0.041. Radians, I believe. Radians. Okay, so that's for the first sub-problem. The second sub-problem is determine the magnitude of the resultant forces at A and B in kilonewton. So this is just from 101. So don't mind the writing muna. I'll explain everything. So una, let's just first get where we can derive forces from. Syempre, we have the weight here is equal to mass times gravity. From 101, if we have one rope, we have one tension. And this is the same rope. So across the whole rope, we should expect the same tension. Same tension. Given that this tension here is equal, but the tension here we know is equivalent to the weight. It follows na yung tension dito is also equal to the weight. The directions slightly arbitrary, but from intuition lang, this should be pulling down. This should be pulling away, like relative to here. So yeah. Here naman is just the reaction support from A is here. And therefore, if you cut yung internal forces mo, magkakaroon ka ng FA dito. And then, for pin B naman, you have reaction force about Y, reaction force about X. So that's that's the initial setup. Yeah, okay, I'll explain the red arrows later. So essentially, if you set up your regular equilibrium equations, you will get these three, right? You can pause at this point just to double check na tama. And then essentially from this point on, uh, we solve first the second equation because W is a known quantity. It's not an unknown. We know W is equal to mg, and we know what m is. It is 2,000 kilograms. Yeah. So meaning we can solve for it. Rearranging equation number two, we get W equals FBY. W is equal to mass times G lang. That's this, that's this. So because it's a positive value, our initial assumption was correct. It is in fact pointing upwards. Parang creating a compressive force on the on this thing, essentially. Yeah. So that's equation 2 done. Equation 3, kung pansinin nyo, this is equal to weight, and we said weight is a known quantity. We can solve for it. So meaning one equation, one unknown din to. So what I did here is I just transposed this to these two terms to the left hand side, and then I just made this W because they're just equal. So 3.75 minus 3.25 was naging positive siya. Ito naman, since positive yung sign, naging negative. Group them together under W because that's equal to T. That's equal to 1.5 meters times FA. Moving things around, you get this. And therefore, FA is equal to 6,540 newtons. So now, we can move on to the last equation, which is equation number 1. Technically, ito, at the start of this problem, it is two unknowns. But because you've solved for FA just recently, we can also plug that in here. So now we have FA, FBX is equal to transposing this 2 to the left-hand side. We have positive 6,540, positive 9,620. Well, I transpose them to the left-hand side and then I swap their places. So like, basta positive yan. You do the algebra. And therefore, this is just 26,160 newtons. So now, that's essentially the second part. I'm drinking water. Now, we are moving on to the bulk of the problem, which is yung designing dimensions. Essentially lang naman dito, we want to find the smallest possible items that still hold, still meet the requirement set. So what are the requirements? Dito may factor of safety, my normal stress, my shear stress, and then my allowable bearing stress. Note that this is ultimate, meaning eventually we still have to find what the allowable normal stress is because design always takes into account the allowable normal stress, the allowable stress in general. That's where the factor of safety will come in, but we can get to that later. So that's what we're tasked to do. We have to figure that out. So I guess before that, run down as to what the types of stresses are para rin make sense what they're doing. So types of stresses, essentially these are variations of F over A because that's what stress is, force over area. And what we are basically just doing with the different types of stress is it's measuring a different area because it's a 3D, because obviously objects are in 3D space, meaning you cannot account for all the 3D space at the same time. So you're taking it 2D by 2D. So mag-iba-iba talaga yung area mo. And therefore, all the different stresses are just different like snippets of the measurement of the total force going through an object, if that makes sense. So, una is your normal stress, which is essentially just you have a force flowing through here and then you're measuring it about the area. kapag bolt and bar or bolt and bracket or basta involving a bolt, usually you wanna first check at the bolt. I think this is called gross or this is called net ata. And then you wanna test at the part na uh hindi involved yung bolt, which is gross. In some cases, let's say yung bar natin nag-shrink pa siya around here. You also wanna test around here. But that didn't happen in this case, so two places lang. Second is shear stress. Essentially, uh, it's this part that's a plane here. So, kunyari, ito yung, uh, this is this, nakatagilid lang. It's essentially the part that juts out, the part that the first section that sticks out kung may bolt ka. That's the one that's subject to stress. So we want to get uh the stress at that specific like area section. Uh, yeah, when it experiences like loads. The third is bearing stress, which is essentially from top view. Ito yun. Technically, it's the one here, but for 102, we idealize it to be the one here. So, sa uh, using the same section we demonstrated for shear stress, bearing stress is essentially here. It's caused by coupling. So technically nga, it's the one behind dito. Pero for 102, it's essentially this area, the one na involved sa coupling or sa bearing, right, ng other thing like coupled to the bar. The fourth thing, but it's not relevant to this problem, but I guess for completeness, this is the last one, punching shear stress, which is essentially your shear stress. But for the like kung bolt and bar siya, shear stress refers to the section of the bolt that juts out. For punching shear stress, it refers to the section of the bar that will basically the way you think about it is dun siya magte-tear off if nag-fail yung system, right? Dun siya bubutas. That's the exposed area if it breaks. So that's punching shear stress. Um, okay, moving on. So for shear stress, um, for all of this, what we're essentially looking lang for is uh a way to what you call that? A way to test na hindi tayo lalagpas sa maximum stress at the different types of stress. And we want to find the dimensions of the bolt and the bar that meet those requirements. Na hindi tayo hindi we can still meet these requirements using the smallest possible options. So, yung question now is, do we first start with the bolt or the bar? Um, the answer is the bolt. And the reason for that is, if we go back to the measurement of normal stress, kita niyo na one of the measurements is across the diameter of the bar, of the butas where the bolt goes in. What this means is that yung normal stress mo or yung normal stress at that point is dependent on the size of the bolt. So parang dalawa yung iisipin mo. Ano yung size ng bar, ano yung size ng bolt. So you can think of it as a like one operation, two unknowns. So that's very difficult to do, if not impossible. Compare this to shear stress or bearing stress. Essentially the bolt measurements, they don't really depend on the thickness of the bar because this is the only part that you're measuring. Ito naman, this is the only part you're measuring, right? This. So hindi siya nagmamatter gaano ka uh, ano yung bar dito, yung height ng bar. It doesn't matter to us because the thickness of the bar anyway is fixed at 20. So di na siya important to us, basically. Yeah. So now, uh, we solve for the bolt first. So meaning shear and bearing stress first. So let's solve for the given the maximum shear stress, what are the dimensions? So essentially, diba, stress is just force over area, as we said. So we can start from there. The force is 6,540 newtons. This is derived from here. Sabi natin, the force about point A is 6,540. That's the only force acting on this bar, right? That's FA. Nandito. Nag-actually. So meaning, yun lang yung kino-consider natin. So then, that's 6,540 over radius, the squared pi. Right, the shear stress measures about the cross section of the bolt, which is this. Kaya r squared, pi r squared. Right? Moving around, some algebra lang, ito yung magiging itsura niya. And this is equal to this, which is equal to 7.214 millimeters. That is not the final answer yet because syempre i-compare pa natin. Di natin alam if itong diameter na to, can it meet the bearing stress requirements? So we have to check both requirements separately. Check muna. Okay. Okay. Thank God. Okay. Bearing. So, sabi, 175 megapascals. That's the requirement na bearing stress na it can handle. That's just equal to, again, force over area. So, 6,540. The difference now is, so nakikita nyo na the difference really now is just how we measure the area. Now naman, yung mini-measure natin na bearing stress so again, bearing stress is this. If you think about it, this is just the thickness. So this is 20 millimeters, right? And this is the diameter. So meaning the bottom term here is the thickness times the diameter. Moving everything around again, you get this final term. Simplifying, you get 1.869 times 10 to the negative 3 or 1.869 millimeters. So you have two options. Again, plug size, usually you pick the larger one because if you plug this into here, kakayanin niya yung maximum bearing stress. But if you plug this into here, there's no guarantee na, it is very likely that the thing will fail. So we picked the larger one. Yeah. So from the choices, we use the 10 millimeter bolt because this problem in particular gives us choices for what the bolt is. So in this case, we choose the 10 millimeter, not the 7, kasi, well, not only do we need to round up, so this becomes, like even without choices, this becomes 8, kasi it's a requirement to round up for design problems. But also, lalag pa siya. The shear stress requirement will fail if we choose 7 millimeters. So ayan, that's for the first part. So now we know that this is going to be 10 millimeters. So that makes our solving much easier for the normal stress. Although, hindi pa natin alam yung allowable normal stress. You only know the ultimate normal stress and the factor of safety. But recall, the factor of safety is just ultimate over allowable. Meaning, we move things around. Allowable is just equal to ultimate over factor of safety. Meaning, our allowable is 700 over 9 megapascals. So now we have a P over A that we can use. So that's essentially just this. And now we have to look for the force. So una, kunin natin yung force across this part. So we want to isolate this into, let's just focus on this section first. So that means na nahati yung force between two different chunks. So that's why you have 6,540, which is just this, right? Same force na ginamit natin kanina, but again, we're looking at a different area, different two-dimensional plane with respect to the problem. So 6,540 over 2, and then we have a given height. We have a given height for this, which is yeah, a given height, and then this is just the thickness. So again, because the thickness is the one, like if you tilt it, kasi the thickness is this one. This is the this is the thickness. This is the thickness. This is the unknown value. Kasi this is fixed at 20 millimeters. Yeah. So now what we get is that this is 2.10. I'll just clean this up. Okay. Tapos this is 10 plus. So why isn't it ito lang? The reason is this 2.1 millimeters only measures this part. It only measures this part. So kailangan mo pa siyang i-doble plus add the diameter of the hole. So that's 10 millimeters plus 2.1 times 2, get 14.2. So that's for this part. That's for this part. The next naman is this part, which is more straightforward. 6540 over height times the thickness. It's the same thing. You get 700 over 9 times 10 raised to 6. That's equal to 700 over 9 times 10 raised to 6, which is our allowable stress in megapascals. And you'll get a height of 4.2 mm, meaning at this section, oh, sorry, normal. At this section, you'll only really need 4.2 millimeters. But again, because we're measuring a bar, yung kukunin natin is yung mas mataas sa dalawa, meaning 14.2 millimeters versus 4.2. So we use 14.2. And based on the table of options here, the smallest one that meets that value is the 150. So we choose both S and bar Y, essentially. Yeah. Sorry, that was a bit quite fast, pero hopefully you can pause and rewind and it will be clear. Okay. So moving on to problem 2. The rigid member NPS is supported by an aluminum rod with these specifications as shown. The system was assembled at an ambient temperature of 25 degrees Celsius while no load is applied. Consider the situation where the temperature changes to 40 degrees Celsius and at the same time a concentrated load P is applied at S. Neglect the weight of the members. And then we have these questions. So the first thing that we want to note is that it says suppose that pin N will stay in its original position after the change in temperature. The reason why this is important is we can use that as reference later. But for now, that's there muna. Wait, I feel like I did not explain something at the start. There, this should be over 2. The reason why is for shear stress. The reason why is because the reason why is because this is double hinge pin. So yeah, you will actually get this when you include the 1/2. Apologies ulit for missing that. I'll just tag it sa video na there's an error. Okay. Sige, sorry ulit. Let's go back. Problem 2. So N will stay in the same place. So the first question is, what is the value of the concentrated load P? The way we solve that essentially is by trying to derive systems of equations to find that point, right? Yeah. So let's just set up a bunch of systems of equations that make this true. that set this problem up. Una is yung traditional lang na equilibrium equations, right? F along y dapat equal to 0. So that's just plus yung h with respect to n, r with respect to t, minus p equals 0. So it should be quite straightforward, right? Plus, plus, minus. And then moment, since n is static, this is actually quite good. Like, di siya mag-change yung sabi, diba? That's part of the question design or the given in the problem. Meaning, this will always stay here. We can use that as a reference for our moments. I mean, technically, you can use any point also, but this is just the most convenient. So, um, yeah. So then you have F R with respect to T. Ito lang yun. Moment of this. And then the moment of T, which is just this. So that's why you get this equation. The last relationship that you have is yung compatibility equation. So that's the second part that you want to check when you run out. Because if you look at this is three equations. Sorry, three unknowns, but you only have two equations. So we can't really solve the system yet. So we'll try to look for more information to relate the moving parts of the problem together. Let's try delta t over 1 with respect to m top, and then delta s over 3. Expressing it in terms of yung PL over AE, this is the force P, the length 1 meter, the area pi r squared, sobrang isang pi. We don't know the diameter or the radius yet because it's not given. Actually, it is a part of the question. So, B sabi sa B ano yung diameter. It's just not given here. And then, modulus of rigidity, which is 200 gigapascals. So, I just converted it to pascals. And then, this is just the point S. So, wala siyang ganito na equation because it doesn't have a bar. Restricted to it. I also just expressed yung movement ni HN dito in terms of yung TL over AE, but it's not part of this relationship. So, moving on, let's move to the first sub-item. What is the value of concentrated load P? So the first thing we want to get is the force muna itself, right? And the way we do that is if we can find a value, for example, for FRT or FHN, maybe that's one way that we can find P. So the way I'm gonna go about it first is just use the information delta n equals 0, but this is a fact stated in the problem. This means that the mechanical component of its deformation plus the temperature component of its deformation is equal to 0. Meaning, if we wait, what I did here is I just moved this to the right hand side. So nag-negative siya. This will be okay. Just wait lang. Mag-cancel yung lengths. So now this I transferred to the right hand side. So naging FHN is equal to A times E times alpha times delta T. So this is just the area, 0.025 squared times pi. This is the pressure, sorry, not the pressure, the modulus of elasticity. Ito. And then this is the parang yung alpha relating the deformation and temperature, and then this is the temperature change. Again, don't input yung temperature, input the change in temperature. 40 minus 25, 50. You should get FHN equals this entire term, right? The important part here is to understand bakit siya negative. So we assumed at the start that this is a upward force because essentially bababa yung buong bar, and therefore like bar NTS will go down, and therefore bar HN will try to resist the bar going down, so it will create a tensile force. But apparently that's not the case kasi negative eh. So meaning the true force applied by the bar HN on NTS is actually downwards, meaning that it's actually doing a compressive force. Mas intuitive tignan pag ganito siya. Pinupush niya si point N pababa because uh, eh, yung reaction is pababa because it wants to pull bar point N, right? Because point N is expanding. It wants to go this way. Point HN is effectively pulling it back, meaning yung reaction force mo is pababa. Right? Because you have action-reaction pairs. So, kaya siya pababa. Yeah. So, meaning, your new like system involves pababa na FHN. Now, now what you want to do is find P. So this is our setup for P, right? This is our setup for the whole problem. If I, for example, set my moment here, ma-eliminate ko yung force along PR, meaning I'm just left with the force along NH and P. So that's what I'm gonna do. I'm gonna set set a moment here, and let me just clean that up. I'm gonna set a moment here, right? M E is equal to 0 is equal to 1 times 48.655 kilonewtons. So just converting it from newtons to kilonewtons. Minus 2p. Just to, para makasunod ang lahat. Start here. This is counterclockwise, therefore positive. Here naman, this is clockwise, so it's negative. Meaning our P is equal to 24.328 newtons. Yeah. Okay. So that's our P. Sige. Now let's move on to the next part. So full transparency. The reason why my writings up until this point is I was recording for a whole hour, tapos nakamute pala ako. So, that's why I tried to be as concise na sa other parts because my voice is a bit strained na rin. Yeah. So, let's move on to 2B. What is the diameter of steel rod RT if the stress experienced by the rod is 150 megapascals? So we want to look for the diameter of the rod given a given unexperienced stress. So how do we relate stress and radius? Well, we can start by just defining again stress. That's just P over A. This is apparently equal to 150 times 10 to the 6 pascals. Now, we can break this down further. Yeah, we can break this down further. This P just refers to the force at P with respect to R. The force of P with respect to R. Oh, okay, makes much more sense. You just fixing conventions. Okay, that should line up now. This is just the expression of P, and then we can rewrite area to be pi r squared or pi, yeah, pi r squared naman. Pi diameter over 2 squared technically, but okay, sure. Para mas madali. Kasi magkakalculate lang naman tayo. So, if we can find Fe with respect to R, then we can essentially isolate D, shift solve, find the answer, right? So that's what we're going to try to do. FTR, so recall na na-solve natin CF NH and CF INCP, meaning this first equation is now usable because it's just one equation, one unknown. Plugging this equation back, plugging in this equation back, we get uh, negative theta. And then I'm just gonna use the rounded values, but I'm like sa solving mismo, these are exact. I just don't wanna write the whole thing, right? F R minus 48.655. So these are just things we have found kanina. 40, ayan, 24, sorry. Let me just, sorry, fix a couple of things for accuracy. Okay. Uh, and then this is just, we found P as well from P. Ay, this is P. So, pinabili na. Right? So, nabaliktad ko lang siya. Pero that's essentially the two. Again, this is negative na pala, di ba? From what we realized, pababa pala siya. So, moving that all to the left-hand side, magiging FE with respect to R, 72.983 kilonewtons. So that's FTR. And then, because we have that now, we can plug that back in here and get D. Sige, I'll just show the setup for it. Sorry. Pero I'll just shift solve it from this point forward. Solving that yourself, you will get 0.24897 meters, which is equivalent to 0.02. So it's equal to 24.89 448,897. So magiging 24,890 millimeters. So that's the diameter of the tube. Because we know the force, we know the force over area, which is the stress. So we can derive the dimensions from there. Yeah. Last, what is the final position of S? Employ small strain analysis. I don't understand why we needed to use small strain analysis because we can use compatibility equations, bringing back the thing that we solved. Ito. Uh, right? Rearranging this is equal to so we can get the deformation or the delta T And then we can find delta S from there. This is good because it's relatively straightforward to find delta T. We just have to split it to yung physical, TL over AE, and then yung mechanical, alpha L delta T. And we multiply that all by 3, right? This is quite good for us because remember, the earlier problem gave us a value for P over A, which is uh 150 megapascals. So that's your P over A already. Right? This is sorted. Multiplied by 1 meter over E, which is just 200 gigapascals. And then you have the thermal 3. Then you have the thermal aspect 17.3, yeah, -6, 1 over degree Celsius times 1 with 1 meter, which is the length, times 15 degrees Celsius, which is the change. And then that's all times 3. So now, makukuha nyo na the deformation is 3.0285 millimeter. So by ES 102 convention, that's 3.029 mm. That's your final answer. Because we just found, so essentially, para lang mas malinaw, ang ginawa natin is we instead of looking for delta S, we looked for its relationship with delta T, and then we solved delta T, right? Delta T can be expressed in a mechanical component and a temperature component. To make our solving quicker, we know what P over A is. It was given in the problem to be 150 megapascals. So we use that here. Then we multiply the length over E. And then we use alpha L delta T. And then calculated to get that. Ayan. Wow. 1 to 2 na kasi. Okay, so whatever. Ayan. Last problem 3. Copy it down here. Compound shaft MAR is restrained at fixed support at both sides. Segment MA is made up of solid bronze with the following G and allowable shear stress has a diameter of 200 millimeters. Segment AR is made up of solid steel with the following modulus of rigidity. And it also has the following allowable shear stress, and it has a diameter of 150 millimeters. It is subjected to a torsional load P naught at point A. Okay, so now the first thing asked of us is to express the internal torques in segments MA and AR in terms of the applied load. I guess just game sense then with like exams. This is the largest chunk of the question, which probably implies that useful siya to the rest of the problem. So this is the very dangerous ladderized problem na yung first step pa lang, if you don't get it, you're kind of screwed. So, sige. So, let's try to first derive some basic first principles. Again, trying to first derive traditional equations and compatibility equations. So, let's do that. Let's arbitrarily assign na clockwise sila. So this is torsion about M, torsion about R. So, meaning Uh, this is just the moments across the whole thing is equal to zero, is equal to moment of moment by torsion m minus t naught plus moment about torsion r that's equal to zero. So meaning the relationship here is that t naught is equal to t m plus tr. That's the only thing we can derive. Kasi this is a twisting question eh. Wala tayong x and y dito. Which might be a good thing. It makes it so much more complicated kung meron. So the next thing we want to find out is compatibility equations. So recall, um, the way we can relate the whole shaft together is if it is if it has fixed supports on both sides, then along the whole shaft, oh my God, wait. The whole shaft, if you have fixed supports, should be zero angular twist. However, we can subdivide the shaft into individual like subparts, which can have like twist within them, right? Sorry. Um, so it also follows na if you have twist about AB, this is equal to twist about AC plus twist about CB, right? Parang nagsingit ka ng C sa loob and then uh, the equation still holds. So because we have two different tubes here, we can use that as reference points. So what I'm gonna do is use the compatibility equation, twist about angular twist about MR is equal to zero. Uh, but then rewrite it to include A. So MA plus angular twist about AR is equal to zero. Okay. The next thing I'm gonna do is try to show it in terms of M and R. I don't want A to be the first term. So yung mangyayari is, I want A to be the sort of reference point-ish. Right? So it's with respect to A. So this means now we have MA minus RA equal to zero. Okay. So now I can represent these into like as other equations. So recall angular twist equation, which is equal to the torsion times the length over the polar moment of inertia times the modulus of rigidity, TLJG. So just expressing all those terms, right? So parang we take this to look like this, and this becomes TM times the length, 1.2 meters, over the polar moment of inertia of M times the given modulus of rigidity, which is 42.5 gigapascals, minus PR 1 meter modulus of rigidity of R. Polar moment of inertia of R. Modulus rigidity is given to be 80 gigapascals. Now, solving for these two, this is a geometry thing lang. Recall na the modulus of rigidity ay the polar moment of inertia is equal to pi over 2 times r to the fourth lang. In the case if you have inner and outer radii are 4, small r4. In this case, this is 0 for us because walang inner radius. So calculating that for both, J sub m is 0.2 squared pi over 2. JR is equal to 0.15 squared per pi. why not? Okay, wait. Sorry, 0.1 should be radius. So 0.75. Okay. So plugging this in, you have a very long equation. So magkakaroon ka ng uh yeah, yeah, diameter siya. So magkakaroon ka ng Tm 1.2 m over 0.1 squared pi over 2 times g, right? And this is transpose na natin. So magiging equal na to. Equal to PR 1 meter 0.075 squared. Sorry. 80 times 10 to the 9 pascals. Okay. Um, this is just, so yung gagawin nyo arithmetically is, algebraically pala, sorry, is magiging, isolate this to BTM. This is equal to uh this whole thing. Okay, thank God my copy paste. And then the reciprocal of this thing, right? That's just what it means to transpose. Transpose lang. Yeah, gets okay. Yan. So then, simplifying all of this using our calculators, we get that Tm is actually equal to 340 over 240 Tr. Baka mas convenient yung kabaliktaran pala. So we might as well get it while we're here. Tr is equal to 243 over 340 Tm. So now, we have a relationship between the two. So recall na what we want is Tm. So so the original problem asks us to express the internal torques in terms of T naught. So meaning, we want Tm to be like something times T naught. So the way we achieve that is by bringing back the first equation that we solved at the start. Ito. T naught is equal to Tm plus Tr. Yeah. So the way we are able to use this is we can now express Tm in terms of Tr and vice versa. Meaning we can make this whole term puro Tm or puro Tr. Arbitrarily, let's do Tr first because ito yung gagamitin natin. T naught is equal to Tm, which is just equal to Tm, right? This Tm, this is Tm. Therefore, we can plug this in. 340 over 243 Tr plus Tr. So, meaning T naught is equal to 583. Saan galing yung 583? 340 over 243 plus 243 over 243. 583 over 243 Tr, getting the reciprocal. Tr is equal to 243 over 583 T naught. So that's the first part. You can either reset this process starting with here, or you can use this fact, right? T naught equals Tm plus Tr, meaning it's like 243 over 583 plus blank equals 583 over 583. This is the slightly faster method. So, makukuha mo na, therefore, Tm has to be 340 over 583. But you can also use the other method, plug in from the start. It's just marginally faster. So that's the answer to problem one. Uh, Let me just clean this up. Okay. Um, we find the maximum allowable value of the torsion P naught. So essentially naman dito, P naught, di ba, applies to both this and this, these two sections. Um, so for this shaft, what you want to check is which one is the weaker one, quote unquote. Alin yung una bibigay. So we will get two individual maximum P naughts, and then the smaller one becomes the allowable value for the whole shaft, right? Because if we reach the smaller value, then bibigay na yung weaker subshaft, right, or section of the shaft. We have to use the smaller value. So essentially, we're solving it individually, and then we're solving it individually, and then getting the smaller value. Okay. So the given that we have is that we have allowable shear stress for both. So let's just do this one by one. Una, hanapin natin for M, which is the solid bronze section. So let me just label this. So we get T naughts of both. Select smaller. Um, so back to our original equation, which is just that uh, which is that um, tau. So this is the tau is equal to torsion rho over J, right? This is the main equation that we'll be using for this one. So getting this will give us the shear stress given torsion given the rho, which is our radius, right? Our radius within the shaft uh over J. Again, special case if we're looking for the maximum, rho just becomes C, which is the actual radius of the shaft. Since we're getting maximum, we'll just use the maximum radius. 50 times 10 to the 6 is equal to Tm times 0.1 pi over 2. 0.1 raised to 5. This is what we got from kanina. Yeah, okay. So then, we have simplifying these values. So magiging 50 times 10 raised to 6 pi over 2 times 0.1 raised to 4 over 0.1. This is equal to Pm. Pm, therefore, should simplify as 78539 0.8161. So, this is not yet T naught, pero this should give us an indication of like what is the maximum PM at that specific point, right? So now, we can keep going. Okay. This doesn't apply here pala, because these are two different sections. So magko-combine yung required force mo on both. Because again, T naught is equal to Tm plus Tr. This is Tm. We'll now look for Tr. So we repeat the same process, but using the values for section R. Yeah. So this is the force. Again, this is That is the torsion times rho, which is the subradius or the radius section. Because again, yung shear stress is proportion like the farther out you go or the larger your rho is, the larger it is. Linear relationship. Since we're getting the maximum case, we'll just get the largest possible value for rho, which is the radius, over polar moment of inertia. So this is just the radius, pi over 275 raised to 4. Again, when you rearrange this is just one equation unknown, one unknown. So idediretso ko na TR is equal to 49,700.97753. So again, these are the maximum torsions for that specific point. But because we've established na T naught is equal to Tm plus Tr from A. Therefore, it follows that T naught is just added together. This is just equal to 119.241 kilonewtons. Yeah. All right. Nice. C naman. Determine, so now we have a different thing. Consider an applied torque equals 100 kilonewton meters. Determine the magnitude of the torsional reactions at the supports M and R. Draw and properly label the internal torque diagram. So, torsional reactions. So, if you think about it, this is roughly the exact same as the diagram we showed kanina. So, I mean, there's this, so the internal torque diagram kasi is like, essentially, yung may paganito. So what that means for us is that we have a counterclockwise at N. Okay, we have a counterclockwise at N. And then, bababa siya kasi you have a clockwise T naught. Right? And then, aakyat siya balik to 0. So, this is what it basically looks like. And then you just fill in the values as we go. Yeah. So, that's basically the torsional reactions. If we try to solve this, again, using this relationship, right? So we have T naught equals 100 kilonewtons. We can just use the relationship here. So using these two, we can find out TR is equal to 41.681 kilonewtons. And then we can also find out now this is 58.319 kilonewtons. So these are just your answers na for C. Quite straightforward sa item. Sa item D, find the maximum shear stress along the shaft. So you will have two, and this one actually magkaiba na. Ito na yung comparing. Hindi pala to comparing. Additive yung una. Ito naman comparing na talaga. So we just basically take T at R versus the shear stress at M. So let's start with R. Uh, Essentially, you get the same equation, diba? Force, uh, T, torsion pala. Torsion times rho over J. Torsion is just TR. We have solved for this. Rho is 0.1. And then J is, we have solved for this as well. So ito lang talaga yung nagbago from the previous iterations, guys. And plugging this in, okay, sige, I'll show it now for the sake of completeness. Okay, this, oh, can make this more, if it's a space. Yeah. This is equal to uh 37.127 uh megapascals. Yeah. So that's the first part. So this is the one for R. For M naman, Tm. So just same equation, plugging in. So again, torsion times rho, which is the radius. In this case, because we're looking for the maximum, we look for max again. Plugging this in, sige, for completeness. This is equal to 62.898 megapascals. So between the two, pipiliin natin is yung 62.898. Therefore, our max rho is 62.898 megapascals. So that's for sub-item D. Last naman for sub-item E. Suppose that a steel segment AR is to be replaced by an available hollow shaft with an outer diameter of 173 millimeters with the same material and same length. Determine the required thickness for this hollow shaft such that the angle of twist at joint A remains the same. So if we want the angle of twist to remain the same, then we want its parang twist equation to be the same. So meaning T old times L old over J old times G old should be just equal to the new version. Pero kung pansinin natin, the tension obviously doesn't change. The length of the bar doesn't change. And because it's both steel, G doesn't change. Meaning we're really just interested in setting up an equation such that the old polar moment of inertia is the same as the new one. Setting up the old polar moment of inertia, we have, I'll just do it in terms of radius. 7.5 raised to 4. This is equal to pi over 2 times, okay, so yung hinahanap is yung thickness. To have thickness, you must first have an inner and an outer radius, right? Because inner minus outer radius is, outer minus inner radius is thickness. So, we first find the inner thickness, the inner radius, so that we can derive the thickness. So una, 865, saan ito galing? This is just the new radius, the outer diameter. I converted it to radius. I just prefer doing it like this. Pero you can also just go straight to the radius. The diameter, that's also fine. Magka-cancel to. You have 0.075 raised to 4 minus 0.0865 raised to 4 equal to negative r to the fourth. I will not bore you with the arithmetic behind this na. From calculator, r equals 0.07021, etc. We're not looking for r. We're looking for the thickness. Thickness is just equal to the diameter, the outer radius minus the inner radius. 0.865 minus 0.07021. This is roughly, so this is all in meters, by the way. So 0.01625 meters, approximately 16. Wait. Yeah, 16. 1.6. So 1.625 millimeters. 626 pala, when rounding. Sixteen nga, sorry. 16.26, 258. Sige na, pagkitay decimal places. Okay, so that's it. That's everything. That's ES 102. I will submit this when I've cleaned up all the solutions. Yeah. At the time of this recording, reminders lang na due today, I guess today now, because it's 2 a.m. Today at 11:59 yung PSQT, so don't forget that. If you have any questions, just reach out. Yeah, thank you and good night.